Hello everyone, in this lecture we'll be talking about X-ray production and interactions with matter. We will start with the main components of the X-ray tube. First we have the vacuum, which will be made of glass or metal envelope. And then we have the cathode side, which is the negative side of the tube. And then we have the anode side, which is the positive side of the tube. Then we have the protective housing, which will protect the tube. Let's get started with the cathode. Here we have the cathode side. It has tungsten filament because it has a very high melting point and a high atomic number, which makes X-ray production more efficient. The filament here in the cathode side, it's made of the tungsten. This is because tungsten has a very high melting point, atomic number, which will produce a very high number of photons. It's heated by electrical current, so the current will flow within this filament, which will heat up that filament. Produces electrons via thermionic emission, and from heated cathode filament, electrons gain enough energy to escape and produce X-ray. So here in the filament, we run current, and that current will heat up the filament, and the filament will release electrons, which eventually produces X-ray. Filament current controls MA. So the filament will control how much MA in that machine or how much milliampere produced in that tube. Now we have the anode side, or the positive side here is positively charged, which will attract electrons to the positive side. Target material usually tungsten or rhenium. Why? Because it has high atomic number, efficient X-ray production, and high melting points. Why we need high atomic number? Because with high atomic number we can produce more X-rays, and from producing that X-ray we will have very high heat in the anode side. This is why you need a high melting point in that material. We can see the disk here, which photons will be produced, and it's made from these materials. The most important is the tungsten. Now we have the focusing cup. The focusing cup is a shallow depression in the cathode assembly designed to house the filament. We can see it here. This is the focusing cup in the filament side. It's made of nickel or molybdenum. What's its main purpose? The purpose of the focusing cup is to narrow the thermionic cloud as they are driven from cathode to anode. Because the electrons are all negatively charged, they tend to spread out or repel from each other. As we condense a large number of electrons, all of them are negatively charged, which will make them repelling each other. The focusing cup is given a negative charge, which tends to focus the electrons to an area on the target. So let's take an example here. We have no focusing cup. This is the filament. As the electrons pushing each other away, we will be having a large or wide beam. But if you're using a focusing cup, this focusing cup will try to focus the electron beam into a smaller area to the anode side. Therefore, blooming will be reduced. This is called the blooming. For the blooming, focal spot size increases or blooms as milliamperage or MA is increased. When we increase MA, which means that we are increasing the number of electrons inside that element, or we're increasing the current, the focal spot size will increase as well, as we can see here. This is our focal spot size. We can see it is very large. Let's take this as an example. We have two settings here. We have the milliampere in how much time we make the tube running or exposing. So 100 MA at 1 second, it will produce 100 mass, which is milliampere times seconds. And then we have another option, which is 200 MA at half second. We increased or we doubled the MA, but we have the time, but still we have the same mass as before. This is because we multiply the MA by the time to get the mass number. So all of them have the same mass, but the one with the lowest blooming effect is the first one, and the highest one will be the last one. Why? Because here we have low MA number, and here we have high MA number. So a quick recap, the MA number or milliampere will control how many number of electrons will go from cathode side to anode side. When increase the MA, we will have a large number of electrons. So as we go more and more with the MA, we will have more and more electrons on cathode side. This will cause a blooming effect because all electrons repelling each other. The radiograph with the best recorded details would be one made with a technique using the smallest MA and longest time. To have a very narrow beam, we need to have a smallest MA possible and longest time. This is sometimes it's not applicable because we need a very short time, and in that case we need to increase the MA. Let's talk about the energy conversion efficiency. What about the X-ray efficiency? We have less than 1% of energy becomes X-rays. Therefore, we have more than 99% converted to heat. So the X-ray is not energy efficient machine because when we put energy into the machine, we only get 1% of that energy to become X-rays, and 99% will be converted into heat. Tube design must focus on heat dissipation and structural protection. So we need to find the technique in our design to dissipate the large heat that we produce in the anode side, and we need the structural protection to protect the tube itself from any break and to protect from radiation, which we will talk about in this presentation. Excessive heat damages the tube. This is why we need to dissipate the heat from the tube. Proper technique selection extends tube life. This is a very important point. Why? Because our technique will decide the tube life or our tube life. When we choose a very high MA number within very short time, this will decrease the tube life in our machine. Now we will talk about the focal spot. The focal spot is the spot where the electrons will hit on the anode side. Small focal spot has high spatial resolution, but it heats up faster, while large focal spot has high tolerance to heat but low spatial resolution. So let's take these two as our example. Here we have a small focal spot and here we have the large focal spot. As we can see here, the electron beam is the same, but the difference in angle between this anode and that anode will make our focal spot either smaller focal spot or larger focal spot. Actual focal spot is large while effective focal spot is smaller. We can see here the actual focal spot will be much smaller than the effective focal spot that will generate our image. Even for the small angle here, we can see this is our focal spot. It will produce even a smaller effective focal spot. So the actual difference between these two is just the angle. When our angle is small, we will produce a small effective focal spot, while if we have a large angle, we will have a larger focal spot or larger effective focal spot. So these two will control heat capacity and spatial resolution. So for the small focal spot with less angle, it cannot tolerate heat, while for the larger one, it can tolerate more heat. But for the spatial resolution, the smaller angle or smaller focal spot, it can produce a good or high spatial resolution opposite to the larger focal spot. Now we'll be talking about the stationary and rotating anode. As we can see here, this is our anode. For the stationary anode used in low output systems, why? Because it's not rotating, it's not dissipating heat more efficiently. In this case, we cannot go with more outputs or more X-rays. For the rotating anode, it distributes heat over larger area, which allows higher MA and shorter exposure times. So the difference between these two mainly about the output. Here for the stationary anode, we cannot go with high MA because we cannot dissipate heat more efficiently. And for the rotating one, we can go with high MA and shorter exposure times. Now let's talk about tube envelope. The X-ray tube envelope contains the cathode and the anode in vacuum. What do you mean by that? This is our tube envelope. It will contain the cathode and anode side in a vacuum. This is very important to remove any interaction to the electron when it goes from the filament side to the anode side. Because if it's not vacuum, then the electrons will interact with the atoms in air when they go to the anode side. Allow electrons to travel freely. As I mentioned before, the electrons, they will go from the filament to the anode without any interaction. Made of glass or metal, prevents oxidation of filament, which will extend the tube's life. Now for the protective housing, it surrounds the tube envelope, as we can see in this image, absorbs leakage radiation. The photons will go in all directions. These are unuseful photons that needs to be absorbed within the tube, except for the window where we need the X-rays to go through and hit the patient to generate the images. We needed to protect the others from leakage radiation that is unuseful, and we leave the window to make sure that the X-rays will go through that window and hit the patient to produce the image. It provides electrical insulation, and also we need electrical insulation to make sure no one in risk that's related to the electrical shock. Now we will move to the tube window. It's thin section of housing. We can see it here. It allows X-rays to exit. We need this window to make the photons go through that window and hit the patient to produce the image. Minimizes the absorption of useful beam. This window should has very low absorbing material because we don't want the photons to be absorbed before hitting the patient. Now we have something called Hale effect. It's variation in beam intensity along anode to cathode axis. So what do we mean by Hale effect? When the cathode side release the electrons and go to the anode side, they will interact with the anode once they hit its surface. So the near surface from the cathode side will have a very large number of electrons, therefore we'll be having a very large photons that are produced in the anode. But as we go more and more deep into the anode, we we will be having less number of electrons, producing less number of photons. This is why we have high intensity or high number of photons in the cathode side, while on the anode side here we have less number of photons. It's caused by absorption within the anode. As I mentioned before, as electrons travels through the anode, we will have less number of electrons reaching to the other side here. Stronger intensity on cathode side, and it's used clinically for thick anatomy. So let's take an example. When we have a patient with a large part and a smaller part, we put the large part on high intensity side. Why? Because we have a large number of photons, and a thick part of the patient will absorb more photons. This is why we need a high photons to go through the patient, not like the low intensity side. Now let's talk about X-ray production. There are two main mechanisms of X-ray production. We have bromistron radiation and characteristic radiation. So when the electrons leaves the filament and goes to the anode side, they will produce X-rays using these two mechanisms. So first mechanism is the bromistron radiation. The electrons deaccelerate near the nucleus, releasing their energy as X-ray photons, which in this one will be the main source of diagnostic X-rays. So the main source of our diagnostic X-rays, it will be from the bromistron radiation. What do you mean by that? When the electron from the filament goes to the anode side, which is positively charged, the positively charged nucleus will try to pull the electron to it, but the electron can escape this attraction and it goes away. But this attraction will deaccelerate the electrons, and this deacceleration will decrease the energy of electrons, but this decreased energy will be translated as bromistron X-ray photon. Why the electron is deaccelerated? Because electron is negatively charged, but the nucleus is positively charged. This is why the nucleus tries to attract the electron to it. Now we have the second type, which is the characteristic radiation. An incoming electron ejects an inner shell electron, and when outer shell electrons fills the inner vacancy, a discrete energy photon is emitted, and its energy depends on the target material. So let's take this image as our example. We have the incident electron comes from the cathode side. It will travel and hit the inner electron in our nucleus or in our anode, and this will be ejected away from the anode. Now we have a vacancy here in this shell. This must be filled by another electron, and we can get the electron from the outer shell. So the electron will goes from the outer shell or L shell to K shell. And the difference between these two energies, because we know that every shell has its own energy, it's fixed, it's discrete. Then as the electron goes from the L shell or outer shell to the inner shell, there is a difference in energy. This difference will be released as characteristic X-ray or characteristic photon. From these two we have X-ray spectrum. It's a combination of bromistron and characteristic radiation. The maximum energy determined by kVb. So we will be having different X-ray energy, and for each X-ray energy we have number of X-rays with the same energy. For example, we have here 25 keV for certain number of X-rays. So for the 50 keV we have less number of X-rays. So it's a spectrum. What about kVb? kVb, it means the peak of our energy, which is the maximum one. Here we have the kVb of 72. So the maximum will be here. It has very low number of X-rays with the maximum keV, and we have another beam with 85 kVb. The number of photons that have 82 kVb, it's very low. Here we can see a peak. This peak is the characteristic X-ray that is produced in our beam. So it's just a spectrum of our X-ray production. We have number of X-rays for each energy in our beam. What about half value layer? What's this term? It's the thickness of simplified material, usually aluminum or for diagnostic X-rays, required to reduce the intensity of an X-ray beam to half of its original value. So half value layer, it's a layer that is needed to reduce the intensity of the X-ray to half. For example, if I say our beam has 3mm half value layer of aluminum, it means when I put 3mm of aluminum in the way of our beam, it will reduce the intensity of our beam to half. It indicates beam equality. Beam with a higher half value layer is more penetrating or higher average energy, while a lower half value layer is less penetrating. As we have high high have value layer for our beam, it means our beam has a high number of high keV energy in our spectrum. So let's explain that in this graph. For example, we have this beam here. It has 1 millimeter half value layer. It means that if I put 1 millimeter in our beam direction, it will reduce it to half. But for this beam, it needs 2 millimeter half value layer. It means that we need higher thickness to remove the half intensity of the X-ray. And for the 3 millimeter half value layer, it means we need more and more to make sure that we can reduce the intensity of the X-ray to half. So for the 3 millimeter half value layer, it means most of our photons have high energy. Also, it's used for quality control. We use it to make sure that our beam has enough number of high photon energy. So what about heat production? We know that about 99% of energy converted to heat, and the anode must dissipate heat efficiently to make sure that it will not break with the time. Tungsten target withstands high temperatures. This is why we are using tungsten element. It can tolerate high temperatures. We can use rotating anode to spread heat over a larger surface area, because when we reduce the electrons and hit the anode side from this side, it will heat up, but as we rotate this side, we can dissipate the heat more efficiently. And we can use copper stem, conducts heat away from the target, and this will make sure that the heat will be dissipated more and more. Heat is released to the surroundings by radiation in conduction. Now we'll be talking about the X-ray interactions with matter. So the X-rays must interact with matter to form an image, deposit those in the patient. So we can use it to form an image, or we deposit those in case of the treatment. Type of interaction depends on photon energy and atomic number. These two will control the interaction or the type of interaction. So what types of interaction we have when we produce X-rays and hit the patient? We have no interaction. One of the types of interaction, the photon will pass through the patient. As we can see here in this image, the photon will penetrate without any interaction. And we have absorption due to photoelectric effect. We can see it here. The photon will go through the patient and will be absorbed or fully absorbed within the patient. And we have the scattering due to Compton effect. We can see here that the photon will go through the patient and will scatter to different direction. So let's talk about photoelectric effect. When the X-ray photon is completely absorbed, we have the incident photon here. It came from the anode towards the patient. It hits an atom within the patient, and it will be fully absorbed by an electron, and that electron will be ejected away from the atom. Inertial electron is ejected. We can notice that in photoelectric, the ejected electron, it will be in the inner shell, and the photon will disappear. As it's fully absorbed by electron, it will disappear from our beam. Photo energy is slightly higher than binding energy. We need the photon energy or the incoming photon's energy to be higher than binding energy of the inner shell electron to knock out that electron away from the atom. It's more common in high atomic number materials. If this atom has a high atomic number, it will absorb more photon. Lower photon energies will increase the possibility of photoelectric effect. And finally, we have high density material as well will increase the photoelectric effect. And it's mainly responsible for image contrast. But also it's major contributor to patient dose, because we are depositing the oncoming photon to the electron, which means increasing patient dose. It produces no scatter reaching the detector because we don't have any photon left. It's fully absorbed by the electron. Now we have the Compton effect. X-ray photon interacts with the outer shell electron. As we can see, we have the oncoming photon. It will interact mainly with the outer shell electron. Photon loses energy and changes direction, but not fully absorbed as in the photoelectric effect. We can see our incoming photon will hit the electron and will eject that electron away from the atom, but still we have some remaining energy into that photon, and it will travel to different direction. Electron is ejected and photon is scattered. We have both. Independent of atomic number and depends mainly on electron density, which is the physical density of the material. So it's totally not related to the atomic number as the photoelectric effect. It reduces image contrast because it causes noise. This scatter photon, it will hit the detector making noise because it's coming from different directions, and this noise will decrease the contrast. Increases patient dose, but not significant as photoelectric effect. So for sure it will increase the patient dose, but not like the photoelectric effect. Major source of occupational exposure. Why? Because the photons or scatter photons will travel in all directions, which eventually will hit the healthcare providers if they are standing without any shielding. So let's sum up the interaction into our table here. We have the dose for the photoelectric effect. Yes, it will increase the dose to the patient, and the Compton effect will do the same but less than the photoelectric effect. We have the contrast. The photoelectric effect for sure will affect the contrast, or mainly contributing to the contrast by increasing the contrast or the image contrast. For the Compton effect, it will decrease the image contrast. For the noise, the photoelectric effect, it will not contribute to the noise, while for the Compton effect, yes, it will increase the noise in the image. For the interaction in photoelectric effect, the photon will interact with the inner shell electrons, while for the Compton effect, it will interact with the outer shell electrons. For the scatter, the photoelectric effect, it has no contribution, but for the Compton effect, it's the main contributor to the scatter. For the absorption, the photoelectric effect will contribute to the absorption, but for the Compton effect is no, because here we have the scatter photon not fully absorbed by the electron. For the occupational exposure, the photoelectric effect has no effect on the occupational exposure. For the Compton effect, yes, it will contribute to the occupational exposure. Now let's talk about attenuation, or the term attenuation. What do we mean by attenuation? It's reduction in X-ray beam intensity, or losing photons in our beam. It occurs due to absorption and scattering. So when I say attenuation, I mean the contribution of these two, not only absorption but also scattering. For the scattering, we can see here it will go to different direction, and for the absorption is fully absorbed by that material, and these two will contribute to our attenuation. Attenuation varies by tissue type. Some tissues will absorb more than other tissues. So what are the factors affecting attenuation? When we have a thick tissue, for sure it will attenuate more from our beam, either by scattering or by absorption. When we have high tissue intensity, for example bone, it will attenuate more from our beam versus soft tissue, which will attenuate less compared to bone. Next, we have the atomic number. When we have a tissue with high atomic number, for example calcium, it will attenuate more from our beam than hydrogen. For the photon energy, when we have a high photon energy, for sure we will have less attenuation from our beam. Therefore, different tissues will have different combination of these factors, which make them attenuate the X-ray differently, which eventually making our image contrast. And that's it for our today's lecture, and I'll see you in the next one.